It's like, hey, cue the existential crisis. Right on time. 2 more semesters.
That I'd be okay with.
It reminds me, I remember that when, in the grad, when he's like, sit still. I can't cancel that again.
I mean, I kind
I
of.
love the Grinch.
I think
Grinch is he's so much more relatable now.
And he just hates
Because
everyone.
he doesn't like people. You know, like, I get
Like,
that.
you know what?
I can relate to that.
He's kind of like,
Yeah, you are.
yeah, barely sitting.
Funny.
Just barely sitting.
Like,
I do.
We were at Thanksgiving, my grandma
I
said the
keep
weirdest thing, and everyone's like, what?
So your impression is he would likely.
Yeah, like, I have to. Everyone's like, how did you know what you were trying to say?
That's the
Anyways, I thought it was like a.
Excellent, love it.
Just like
Just
a person,
well,
like a-
to me, it's like art to make it
Oh, obviously, how does it that about?
like what the thesis.
I can have so much after 4 assignments.
Yeah.
Does everyone else
Even in
like
terms of like.
Oh.
But bullet point, you do this first and then do this, just so the overall picture.
Beforehand and after?
It's like they're like. Cause I'm still like a little bit confused on what it would be about.
We're so
I'm sure
like.
That makes sense.
But then your title.
Consistency.
Right. Using PC. Okay, can you send that?
You guys are my canvassing.
Folks, you want some assignments? Got some assignments, yes? Are they all up here?
There you go, done.
All right.
Yeah, that was fast, okay, thanks, man.
Okay, so the plan for today is, you have to tolerate me talking about regression for a little while. And then we'll be able to do a little bit more on the final exam review. Okay, and answer any questions and stuff like that. Some of that stuff is on regression, but as I said last time, a very small part of it. So, we'll address that, okay? Tell you what you have to know for Monday for that stuff. Okay. So we're gonna skim through this actually pretty quickly because it's gonna be developed in a lot more detail in the spring course. Okay, so for those of you taking the spring course, the spring is almost all about regression. But you'll only learn why it's all about regression if you take the multivariate course. So if you ask the multivariate students, say, why do we have to focus so much on regression? They'll be able to tell you now. So it's kind of complicated that way to understand where these things fit. Okay. So, what is regression? So in skimming through this, I'm doing this as well because I know some of you won't be taking the spring course and you have to have your foot in the door for regression and multiple regression and stuff like that. So we're gonna go fairly quickly through the main points. So what is regression? What's regression for? Well, if we draw a scatter plot, and there's X and there's Y, and we have some bivariate data. What does it mean to say that data is bivariate? Well, it's data that's on X and on Y, right? So this point here is a score on X, and it's a score on Y, okay? We saw this before a little bit, where what did we compute on this already? We computed the covariance, right? And then we said the covariance is unstandardized, so we standardize it, and we got what do we get? Pearson R. So we computed Pearson R on here, and that would be a positive correlation equal to about what? I don't know, maybe 0.6, something like that, maybe 0.7, somewhere like that. And the way to tell how much correlation you have is to draw kind of like an ellipse like that. Okay? So there's the correlation. So here's the motivation for regression. Okay, the motivation for regression is that if I wanted to make a prediction for Y, okay, so if I wanted to make a prediction for Y, well, how can I make the prediction? Well, if I choose a particular value for X right here, Okay, so these are different values for X. For this particular value of X, okay, let's name X. What do you want to name X? Let's give it a name. Variable name.
Age.
Age. Okay. So this is age, and what's Y? What are we trying to predict based on age? Income. Okay? So the 2-year-old is not making very much. But there's the income here. But you know, they probably still get an allowance, so that already the money's starting to roll in. So they're already realizing how the world works, right? So okay. So introduction to money at 1, by 2, starting the portfolio to forever until they're completely corrupt by the age of 70, and it's all about the stock market. Okay. So if you look at, let's pick a, you know, maybe age 16. Okay, so age 16, how are you going to predict the income level for someone at age 16? Well, if the data, okay, I'm just going to erase this just for a second. If the data looked like this, how would you make the prediction? If it looked like that, how would you make the prediction? You'd say, you know what, for someone age 16, that data point right here is equal to whatever income that is, okay? Maybe at that, they're only making 5K, like that, okay? So that would be a nice, neat functional statement because everything is falling on the line, right? Everything's falling on the line. So the best prediction here would definitely be this particular data point. And if we wanted to, we could actually draw the line here and we say, wow, that's a perfect situation, right? It's perfect. It's ideal because all the data points fall on this line. But if that doesn't happen, I mean, why doesn't it happen? Why does our data look like this? Well, that's because of what? Uncertainty, right? We have uncertainty. Okay? We have uncertainty, we have messy data, right? Remember at the beginning of the course, we said it's because it's a big mess, right? It's a big mess, that's why we need statistics. So we have uncertainty around the line, right? We have uncertainty around the line. So how would we figure this, right? How would we figure this? Well, we'd say, for age 16, all of these values are what? Possible, right? All of these values are possible, okay? They're all actually quite reasonable guesses for what the income should be. That number includes 5,000, but it also includes other numbers as well. Because what do we have here? We have a distribution of values. Right? We have a distribution of values here, okay? So again, messiness makes us have to do something a little bit different. What would be the best guess? Well, the best guess would probably still be 5K. Would probably still be 5K. But we have to allow for the idea that we do have error around our prediction. And we have error around our prediction. So we see the logic of this regression procedure is because you don't have a perfect setup and you have variation around the line. Make sense? Make sense? Yeah. So the idea of regression, really simply, is to say, well, before I drew this line, you know, my data looks like this. How do I know where to draw it? Right? I'm even going to change the data now, so it's not the same exact line. I'm going to like put more points over here. How can I fit a line to that data that's going to, in some sense, help me predict income? Right? How am I going to fit a line to that data that's going to allow me to predict income? Where should that line go? Where should it go? Yes. I mean, I'm going to draw a line then. I'm going to draw one line, and I'm going to say, well, I'm going to put the line here. So I'm going to put the line right over here. What do you think of that line? Is that a good line to make predictions from? And I am going to say, for age of 16, the predicted income, right? For age of 16, the predicted income is somewhere up here. What do we think of this line? Just kind of intuitively looking at the picture. Is that a good line?
It's a little too
Right, it's too high, right? It doesn't seem to do what? Well, it seems too high. It doesn't seem to account for all of the data. Well, I'm gonna pick a different line. What do you think of this one? Probably too low. Now, why are we saying it's too low or too high? Let's see if we can operationalize this a little bit better. Doesn't seem to summarize the data, right? It doesn't seem to provide an adequate summary of the entire bivariate data. So intuitively, if I choose a different line here and I put it right over here, everybody's probably gonna agree that, you know what? We like this line better. We like this line better, right? This is a much better line. Now, let's work in reverse now. Now that we've identified a line that we go, that one seems to be better, let's unpack why we think that line is better. Let's see if we can kind of operationalize why it's better. What's so good about that line? The red line. What's so good about it? Well, what's so good about it is that if you take deviations of all these points from the line, right? Deviations of all these points from the line, so these are all deviations from the line. So what does the line represent? Those are all predicted values on the line. So for age 16, what would be our predicted value? We'd read it right off the line, and it would be equal to, it's the same one in this case, equal to 5K. Make sense? It's equal to 5K. What about for an age of 2? How much income? Maybe 1K, okay, well-to-do child, 1K, right? 1K right here is the best prediction, but we can see that even in making those predictions, we're gonna be off a little bit because there's some scatter around the line. So the idea in fitting this line is we fit it in a very, very particular way. Okay, can anyone identify what that particular way is? What function are we kind of satisfying that defines where that line should go?
Variation above is equal to variation below.
Variation above is equal to variation below. Variation above is equal to variation below. Absolutely. Let's see if we can kind of redefine this a little bit better. All of these deviations, we want to unpack with that, what he said is, we want to unpack all of these deviations so that this line kind of accounts approximately equal for deviations above and deviations below, right? We want the line to kind of be what? Like almost like a balance point, right? Almost like a balance point, so that deviations above are kind of balanced out with deviations below. Does that make sense? So intuitively, again, was motivated by intuition first. If I did this, if I added a point here, I'm gonna put you remember these lines were like so out of line that we just, they're just not good. So I'm gonna put a point right here. What happens to the line? Tell me what the line's saying. What's the line saying? So I added another point to the data. What does that line, then the line communicates to that point. Right, what does the line say to that point?
The line wants to go lower in
Right.
reflection of the.
What's it saying to that point? Make the line speak. Right. What's it saying? It's saying, hey little buddy. Right? What's it saying to this point? It's saying, don't worry, I've got you too. I've got your back too. So what does it have to do? If I want to include you in this summary, what do I have to do? I have to take this line and I have to adjust it a little bit, right? So this line here is going to, what's going to happen to it? It's going to kind of shift a little bit downward because it has to account for that point too. It has to account for that point too. Now, does that kind of sound familiar? What other thing have we looked at in statistics where if you change a data point or you add a data point, that something shifts because it's very, very D? Yeah, the mean, right? Does everyone get that? The mean. So if I have, if my head is the mean, and there's data points on this side, data points on this side, and you add a data point here and it's pretty extreme, what happens? I go this way, right? Same thing if it happened here, I have to go this way. Why do we say the mean is democratic? Because everybody's opinion is included, right? Everybody's opinion is included. It's got to adjust for everything. So we look at that line and we say, well, that's what that line should be doing, is providing a summary for all of the data in some sense that it's kind of a balance point, right? It's kind of a balancing line of all these deviations. All these differences from the line should be in some sense balanced. And it's the same idea as the balance point being the mean, okay? The balance point being the mean. So if we were to give a name to that point, it would be called, or the line, we can almost call it, this is kind of, it's kind of like a metaphor, but almost like a floating mean, right? It's almost like a floating mean for different values of x, right? For different values of x. Kind of like a floating mean so that some function is satisfied here in defining it as, we'll define it as the line of best fit. The line of best fit, okay? So that's the line of best fit, and it's going to be called the regression line. It's going to be called the regression line. You want to see the first regression line arguably ever, okay? Well, original data set in 1886 by Galton, was a eugenicist, and trying to see if there's any way that you can get quantified generational transmission from one generation to the next. Eugenicists at the time were very interested in seeing if you can kind of see if, with the biological movement, try to see if there's things like heredity and stuff like that, that are traits transmitted to different generations. If you take two plants, what does that result in the next plant? So all of this stuff, this is where correlation actually came from. Didn't just appear in a book somewhere, but this is what Galton was working on. We have heights of adult children, and then we have heights of the average parent. So the mom and dad averaged out. And here are all the data points in the plot. Looks exactly like that idea. And what Francis Galton did, there he is there. Yeah. Okay. Pretty serious looking person. Okay. Yeah. Francis Galton said, you know what? Let's fit a line through here and let's call it the regression line. Okay? And then sent it off to a mathematician to confirm that that line actually represents a type of floating average. So that's one of the first scatter plots ever. So there's scatter plot without the history, there's the parent, and there's the child, and we have a whole bunch of points. And this kind of makes it clear too that if you look at, for a mid-parent height of say 70 inches, what's the best prediction for child? Well, there's a lot of values that are possible. There's a lot of values are possible. So in a sense, we're kind of like taking the average value, but it's not just the average of that particular column, it's the line of best fit that's going to provide that floating average across the board. Does that make sense? And that's what we're calling the regression line, the regression line. It used to be called the line of reversion, and that was later called the regression line. And what do we, I mean, why is it called regression? Why is it called regression? Well, because if you have very, very high parents, very tall parents, or very, very short parents, what happens with the regression line is that usually there's a regression towards the center of the distribution, towards the mean of the distribution. And that's where that's coming from. Okay, so there's a lot of historical motivation. If any of you look at that, say, I'm really interested in the history, then talk to me, we'll do a dissertation together on it, okay? But that's the whole idea behind regression. Now, the way to think about this, about regression, the meaning behind it is to think of it like this, with the time change. Time change happened on November 1st this year. So, you know, you set your alarm at 7 in the morning, you get up, you've got your circadian rhythm and everything's going to plan. You know, drinking tea at 10 o'clock, sleeping by 10:30, everything's going to plan. And then the time change happens. So what happens, right? Well, the first day of the time change, you go to bed, you say, well, I haven't really noticed anything yet, we just changed the clock. So you still try to go to bed at like 10:30, or you even adjust for it. You even try adjusting for it. But what happens? What time do you wake up? Maybe it's not noticeable yet, but what happens? You wake up at a different time, or you wake up early, you wake up late, right? And that's in the sense, your body's just not, I'm not into it yet, right? I'm not into the change yet. I'm still gonna try going back to what I've always been doing, at least until 6 months ago. Okay. So you think of that in terms of that reversion towards the mean, that regression towards the mean idea, okay? So here, we compute a line, right? We compute a line, there's the intercept of the line, there's the slope of the line, and there's the input value. So there's the value on X. So for that particular value, that would be the value for parent, right? So for an input value of 68, what is the predicted value for child, right? What is the predicted value for child? Well, let's look at this equation. Why is this equation the way it is? Well, it's the equation of a line, that's the intercept plus slope plus x. So y equals, sometimes the line is spelled mx plus b. Well, I would say a intercept plus bx. But you notice something else in this equation. What else do you notice?
Errors.
Yeah, you notice the error. And we say, well, you've seen that before. And why is the error there? Well, we'll see in stat 2 in the spring, we'll see that regression and ANOVA are almost identical. But you look at that error and you say, oh, wait a minute. I know what's going on with this error. Why do we need an error term? Why do we need an error term here?
To account for the noise?
To account for the noise. Could we be more specific? You're absolutely right. To account for the noise. What noise? Look, devil's advocate. What noise? That line's pretty, there's no noise in the line. I mean, it's not perfectly drawn. There's a little bit of squiggly in it, right? But it's not bad. We don't want to be sticklers. So, I mean, if we do this here, I mean, yeah, it's not perfect, right? Definitely not perfect, and it's like, but it's not bad. So what's the noise thing? What noise? Where's the noise? Yeah, the noise is all the data around the line, right? So you've got all these empirical observations, and these are empirical observations based on data, and then what are you imposing on that messy data surface? An idealized line, right? Idealized line that goes, the line comes in and says, I'm the ideal, I am the master of all, the rest of you are noise, right? So the data is what you collected, but now the line rules. Okay, so you think of that in terms of the general idea. We have empirical objects, but we fit mathematical forms to them. It's the mathematical forms that are gonna kind of run the show here. So if you don't like thinking in theory, that's gonna be tough, because it's like, it's actually, you gotta buy the fact that that's a theoretical form. The perfect line does not exist anywhere. It's a function, it's up here, just like the normal distribution does not exist anywhere. It's all in here. So there it is. The rest, it's all noise. So let's think about this now. We've got the E. So there's gonna be some error in prediction for a value of X. You put in, you're gonna get a predicted value, so Y prime sub I. Y prime sub I is the predicted value, but there's also gonna be some error in prediction because of the noise, because of the scatter. If I take this idea here, and I go back to our original idea, and I just draw a perfect set of points, and I do this, how much noise, it's not perfect, but it's a different point. How much noise do we have? Zero, right? We don't have any noise. So we don't have any noise because everything fits on the line. Everything fits on the line. In this particular case, for this particular data, if we were to compute a regression equation on this, our error term would actually be equal to 0. Enter reality of how most things are is this. So you can appreciate, right? You can see statistics are for messy situations. They're not for this, right? They're not for this. That's why statistics are more often used in the social sciences than they are in in physics, because physics is pretty accurate that they don't get that much messiness than they do at the smaller levels, but in many cases, their function statements are actually pretty clean compared to things like this. So, input value, we're gonna acknowledge we're gonna have some error, and what do we get? We get a predicted value. Okay, we get the predicted value is 67.89. So we can say that for the height of 68 over here, the predicted value is 67.89. So 68 for the parents around here, and there's my predicted value for the child height right there. Okay. Notice one thing from this too, right, and it kind of serves as a nice example. We might not even have data for 68. Not have data for 68, yeah, we can still get a predicted value. That's the same thing with averages, right? We get averages, and how many people on average live per household? 3.45. Doesn't exist, but we can still get the average. So that's how regression works. Now, let's identify, getting back to that line, how do we know where we should put the line? So we know it intuitively, and you corrected me, you said, well, bring it up, bring it down, do this to it. But let's identify what this function, this regression line is accomplishing that makes it so popular. So I'm gonna just do this. I'm gonna pretend like there's just 2 data points. Okay, so one data point is below the line, and one data point is above the line. So here and here, what is that line doing? Well, it's balancing those 2 points. What are those 2 points? Now what we can call them is what? An error, right? There's one error, I'll just use a little e. One error and another error, right? One error and another error. The noise, that e at the end, we're gonna call it an error. It's not an error in recording, it's just deviation, similar to an ANOVA, right? In ANOVA, we had the error term. The error didn't say, well, it must be like a mistake. It just meant, hey, that's just deviation, what we're talking about, right? That's just deviation. Within cell deviation, right? What was within cell deviation? Within cell deviation, why were these points different from one another? Well, there's error in there. Makes sense, right? Same concept here, same concept that we have error for different values of our x variable, our predictor variable. So, what function should we specify to make sure that we're fitting that line in the right spot? Well, how about we start with a summation? What would be true just with those particular 2 points? It's powerful, just look at those 2 particular points. What should be true about those particular points? The sum of those errors, I'm gonna use a sub I, because the sub I, this is error number 1, this is error number 2, which is why we need the sub I, makes sense, right? Error 1, the if error. I equals 1 error, I equals 2 error, etc. What should that sum be equal to? If it's a nice balancing point, nice balancing line, should be equal to 0. Makes sense, right? It makes sense that the sum of these errors should be equal to 0, right? The problem is that's fine, but the problem is that we run into the similar problem as we do when we calculating a variance. The sum of deviations from the line are gonna equal 0 all the time. So if by the place we put this line, the sum of errors is gonna equal 0. So instead of taking the sum of the errors, what are we gonna do to them? We always do it, square it, right? Never go wrong with that. Guess C on the test, right? Just square them, right? You sum the squared errors, are they gonna equal 0? No, they're not gonna equal 0. Okay, so let's put in more data. What are the sum of squares? Sum of squared errors gonna equal to? Well, we don't know, right? We don't know what they're gonna equal to. They could equal 50, they could equal 100, they could equal 150. So let's specify a criterion for the line that this line is gonna be fit in such a way that this is equal to what? What should that be equal to? Well, it can't be equal to 0, because no line's ever gonna do that. Because as soon as you start squaring the errors, it's just not gonna work, right? Why is the squaring of the errors not work? Take this error, square it. Take this error, square it. That's not gonna equal 0, because by the operation of squaring, you're getting rid of the negative. Make sense? So this is a negative error. Let's say this error is -1. That's -1, and that's +1. If you sum the errors, what's it gonna equal to? 0. If you sum the squared errors, what's it gonna equal to? 2. So that's the idea when we take the squared errors, just like when we're computing the variance, we get rid of that problem of it always summing to 0. But now we have to say, well, what's gonna satisfy the line? What's gonna be a good fit for that line? Well, we want the sum of squares to be equal to, can't be 0. What would be a better line? Let me just give an example. Sum of squared errors is equal to 100 or 10. Which one do you prefer? 10. Does everyone get it? Why would you prefer the one that has 10? Because that's actually accounting for the data better, because the sum of squared errors is smaller, right, than the other one. So the line salesperson is coming over going, I'm gonna sell you a line. I say, I got a big mess, it's right here, it's a big mess, and I need a line from which to make predictions, okay? I need a line from which to make predictions. So then the line person says, well, I've got one line here, we don't use it that much anymore, but it used to be popular when we used to use Commodore 64, and here it is, 100. I say, do you got anything else? I got another line here, just let me get it. I've got another line right here. This is pretty new, and it keeps the sum of squared errors for this particular data set equal to 10. Which line are we buying? The one that equals 10. Does everyone see why? That makes sense, right? Because if you take the one that has 100, then on average, you're making a lot of errors in prediction, right? You're making a lot of errors in prediction. If you take the sum of squared errors is equal to 100, then what does that mean pragmatically? That means that, the person's 16, what's their income? I don't know, let's make a prediction, we're probably gonna be off. God, there's a lot of noise around, there's a lot of errors. So that line that we're using in this particular case that yields a sum of squared errors equal to 100, that's not that good. This one's definitely better because that implies for predictions on average, we're gonna make less error in prediction, okay? Person's 20 years old, what's your income? Prediction, 15,000. Okay, that's my prediction, 15,000. What's your actual income? 15,500. Oh, not bad, that's good. That's reflected by keeping that sum of squares errors to the smaller value. Make sense? Okay, follow the discussion, right? And then I say to the person, I say, this is good, I like where we're going. 100, 10. I say, give me a line, this is wonderful. Give me a line that has 5. Give me a line that has 5. Give me a line that keeps those sum of squared errors to 5, because that seems to be the better case. What was the person saying? Remember, I've given this person my data, so they're trying to fit a line to it. Trying to sell me a line. What are they telling me about that line? I say, can you get a line that keeps the sum of squared errors to 5? Because I would want that one over this one. And what do they say? They say, nope, 10's the lowest we can go. Make sense? 10's the lowest we can go. I say, well, you're not a very good line person, right? What do they say? But before throwing me out of their store, right? You're not a very good line person. What do you know about lines? What do they say?
It's your data.
It says your data. Bring me a better data set and I'll give you a lower sum of squared error. Okay. In other words, what the person is actually saying, does that point resonate? It's like, can you give me 5? No, I can't. So what the line person says to me then says, I challenge you to find anybody else in the world who can give you 5. Then you're gonna come back to me and you're gonna say, looks like 10 for that particular data set is the lowest we can go. It's the lowest sum of squared error that you can go on this mess. If you bring me a cleaner data set, we can get a lower sum of squared error, maybe get to 5, maybe even get to 0 if it's all along the straight line. Okay. Makes sense. So what's the concept here? That this line is fit in such a way, right? This line is fit in such a way that it keeps the sum of squared errors to what? What's that?
Just minimum.
Minimum. Okay, the key word is minimum. It keeps it as small as it can compared to any other line. Right? Keeps it as small as it can compared to any other line. And for this particular data, the line person says 10's the lowest we can go. It's the lowest we can go using the best line possible. Using the best line possible, the sum of squared error of 10 is the lowest you can go. It is the minimum quantity that we can achieve using my best line. If I say to the person, how about we use a different line? Well, I can get sum of squared errors of 10, but that would be a different line, not as good as this one. So the salesperson says, I recommend you use the best line and you just tolerate 10, but the rest is gonna have to come from you if you wanna get it down low, okay? So the key word is exactly what was just said. The key word, put it in, is min, okay? Keeps it to a minimum. The least squares line, the regression line, is the line that keeps the sum of squared errors, okay? Keeps the sum of squared errors to a minimum value compared to any other line that you could conceivably fit to that data. Make sense? That's why the least squares line is so darn popular. Now, why did I call it least squares line? It's also called the least squares line. Why do we call it least squares line? Well, you can answer that now. Regression line, least squares line. Why are we calling it the least squares line?
Because it's the line that fits to minimize the error value.
Yeah, minimizes the squares, right? Minimizes the line that makes the squared errors a least value. Least squares. Right? So it's, the least squares line is this line that's perfectly fit that makes the sum of squared errors, minimizes the sum of squared errors around the line. And that's what a lot of mathematical functions do. When you apply them to data, you're seeking to minimize or maximize some quantity of the data. But recognize that the line can only do so much, right? The line can only do so much. The rest is gonna have to come to your data. So if I go back to this Galton messy data here, just informally, how well is that data gonna fit? How well does that fit that? How well does that line rather fit that data? Does it fit it well? No, it doesn't fit it well, right? It's actually, you know, it's like, oh, so all the data's all over it. How well is this line accounting for the data? Not really that good. But it's accounting for it the best it can in the least square sense compared to any other line you put to that data. Right, that's the principle, right? I'll just repeat that, is that, you know, if you show this at your dissertation and you go, I've got this awesome least squares line, it's gonna take care of everything, right? It's gonna keep the sum of squared errors to a minimum value. Is this keeping the sum of squared errors to a small value? It's gonna get a minimum, but your errors around the line are still gonna be what? Large, right? Large, not the line's fault. That's the key. It's not the line's fault. It's, well, your data, maybe the nature of your data. So the line can only do so much, right? A good comparison in sports and stuff like that with, you know, when a sports team isn't doing well, who gets fired? Like the coach, right? They don't even step onto the field or the ice, but it's the coach who gets fired. Can we draw the analogy? What do they look for when you hire a coach for a sporting team? You know, the coach comes in, you know, what's your best advertisement if you're chosen to be the coach? And you tell the ownership, you say, hey, you know what, I guarantee your team's gonna win, I guarantee, right? Probably not. What do you actually want to tell them? Well, what's the most you can actually say? Think about it. We'll draw the analogy. It's a really useful one.
I've won in the past.
Well, I've won in the past, sure, but those were with good teams. I won in the past and they had good teams, right? So, what's his name? Bellucci? No.
Belichick?
Belichick, right? Belichick. Bellucci's someone else. Yeah. Bellucci's like, yeah. Belichick. So Belichick says, has a fight with Tom Brady. That's it. You're gone. I'm switching teams. I'm going over to some like Kansas City Chiefs. I think those are the football team, right? So go over. I'm a hockey person, so I don't know. But goes over to the Chiefs, and the management says, "So you've done really good with the Patriots. So you can guarantee wins all over the place." So what does Belichick tell him? What's the key to Belichick saying I'm a good coach? Is it what? I can't, here's what Belichick says, I can't guarantee we're gonna win. I can't guarantee we're gonna win, especially not in the same division as Tom Brady over there who we just left. I can't guarantee we're gonna win, but what I can guarantee is what?
I'll get the best out of it.
I'll get the best out of your players. I will maximize our chances to win. I will maximize our chances to win better than any other line, right? Better than any other coach. Why? Because I'm a maximizer. I'll get the most out of our players. I may even get coach of the year, even if we don't even make the playoffs, because your team is so not good that I'm still gonna get the best out of them, and even getting 50 points is a miracle, okay? That's the same thing as this line is advertising. I'm gonna do the best job it can do, but if your players look like this, it's still not gonna be pretty. It's still not gonna be pretty, okay? In the case of minimization, you can say that the coach, instead of maximizing the performance, I'm gonna produce the minimal errors we can make on the field, on the ice, whatever, compared to any other coach. And that's the best you can do, right? That's the best that the coach can actually advertise, because the coach can't make good players or bad players into good players. And if you don't have Tom Brady, well, then let's do the best we can. That's the spirit of the regression line. Okay. Yes.
So is there any, obviously, regressions for predicting values? Is there any other reason that you do a regression? Like, do you get any information from like comparing regressions of data between?
Yeah, you can make comparisons of regressions between data. You can take like one data set, compare its regression to another and things like that. So you can do a lot more with it. But the two central goals of regression is to be able to predict based on some variable here what the outcome is, what the outcome will be, but also to see how well the data actually are linear and fit a line. Right, so we're gonna need a couple indicators that we talk about more in the spring. We're gonna say, well, how well does that line fit the data, right? So maybe you hypothesize that the relationship between parent and child is linear. Well, fit a regression line to it, and let's see how well that line fits. Because if it doesn't fit well, maybe the data aren't linear. Maybe it's something else. So in that sense, you can use it as a hypothesis testing tool, but you can also use it for prediction. And I mean, usually the motivation behind it is for prediction. Now, when do we want to make prediction? Well, your computer makes predictions all the time, gets the email, contains like blah, 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 blah. Computer predicts what? Spam, right? Slightly different setup, but same principle. Here's one type of email. Here's another type of email. Just make this into two values. Prediction into spam versus inbox. Spam versus inbox. You go to the doctor and they see something in your brain and they say, I'm not sure, is that a tumor, is it not a tumor? Let's apply a statistical model of things that look like that or get a blood test or whatever, and let's make a prediction as to what it is. Okay, so the predictive aspects, it's pretty big business because you're taking data that you have and you're trying to make the prediction of the outcome. Okay. Now, just to stop here for a second, is sometimes you look at this and you say, well, Mr. Galton, you have the parent heights and you have the child heights. Why do you want to fit a regression line to it? And usually the regression line is fit so you could predict what? The observations now? No, you want to predict future observations, right? Based on this data, right? Based on the data. So you'll say, well, I can make predictions on this data set, but really what I'm interested in is if I sample more data that come from a similar population as this data, can I predict to parents what their child will be in terms of height? Can I predict the IQs of children based on height? And you think of it, you probably do that as a clinician. Informally, risk factors for disease, for depression, for anxiety, right? So someone comes in, well, predictions of suicidality, right? Well, what's your prediction for suicidality for this individual? Well, were your parents suicidal? Do you have a history? Well, maybe that changes the prediction a little bit. So the regression idea is rampant throughout all of statistics, throughout all of modeling, and the central basis for it is because we don't have something nice and neat. If we did have things nice and neat, then all this least square stuff wouldn't be necessary, because if everything fell on the line, then we'd be fine, right? We'd be fine. We'd just say, just take the observations and read them off the line. Now, let's just look at one brief point here. This question will come up, if it hasn't already, is, if your data look like this, let's say your data look like that. Just 4 data points, just as an example. Here's the devil's advocate to this says what? That 5. Says this, you know what? There, like that. Who wants to fit a least squares line to that when I could just do this? There's a good fit. That fit actually does better than the least squares line. So after I try to minimize those errors with the line salesperson, say, well, 10 is the lowest they can go with that line. The least squares seems to be the best computer out there. It's the best TV out there. It's the best that. And then I get somebody else, comes knocking on the door, say, I can sell you this. Oh, boy, look at this line. It's not a line, but look at it. Look, say this, how much error around this line? 0. Okay, so then you say, my goodness, that line person, forget them, I'm going with this stuff. What's the problem with that? That person at your door who's trying to sell you that is what? Yeah.
It's not useful for making predictions.
It's not useful for making predictions, right? And what you should actually say to that line person, that is like advertising like a vehicle that's gonna fall apart in 2 years, but look shiny, right? That's what that is. That's like, hey, you can buy this, yeah. Sure, it looks nice, but the parts in there are so cheap or something like that. So that's what this is. This fits perfectly, but it's absolutely useless. And what we would say there is we're overfitting the data. It's overfit. Try making predictions using this, it's not gonna work very well. So this is not as good as something like that. Okay, so, and also you could say, well, hey, my 2-year-old, speaking of the 2-year-old, my 2-year-old could connect the dots, so I didn't really need any sophistication at all. I could have just connected the dots, but I'm looking for a tool that on average are gonna keep the predictions to a low value. Yeah, go ahead.
So are there ways to determine like the power of your line of best fit?
Yeah, no, there definitely are. There definitely are in terms of how well of a fit it is, right? Those are, yeah, we're gonna have to at some point look at that line and we're gonna have to say, well, how good of a line is it, right? How good of a line is it? And that's where we're gonna have to get into measures of model fit, which will be coming up in the spring. But definitely those are good questions. Say, well, how powerful is this line? I mean, how well does it fit the data? So we do need to measure model fit. I mean, I'm gonna just give you the advance on a little bit. What should it kind of be similar to? What you're really asking is, what's the effect, right? What's the effect? How well does the line fit? Well, we already have one of those things from ANOVA, as we slowly slip into a little bit of review too. In ANOVA, what do we have in ANOVA for assessing how well does our ANOVA kind of fit? Well, we have eta squared. We have eta squared in ANOVA provides us that effect size measure. In regression, that measure is going to be r squared. Okay? It's going to be r squared. And r squared is also going to have a range between 0 and 1. And a line that fits perfectly is going to have an r squared of 1. And a line that fits horribly is going to have an r squared of 0. And you can't have a negative r squared. It's going to be between those two values. But that's that idea of how well does that line fit? How well does the line fit? Okay, so let's just leave that for a second and let's pretend that we have computed the least squares line. Okay, we've computed the least squares line. Okay, so there's our least squares line. We can see we can use it for predictions, but we want to ask another question. We want to ask an inferential question about the line. Okay, well, what would be the worst possible line to have? It would still be the line, but what would be the totally non-exciting line to have? The totally non-exciting line to have would be this one. Okay. That line there would be completely boring. Why would this line be completely boring? Associated with X and associated with Y. Try making predictions using this, what do you get? You get the same thing all the time. And for reasons we'll talk about in the spring, this value is going to be the mean. It's going to be the mean of Y. So if your line actually turned out to be like that, that's a flat slope, it has a slope of 0, then no matter whether you're 2 years old or you're 15, how much are you making?
The same.
Yeah, you're making the same thing. You're making the same thing, which is the average of the income values, okay? If that's the case, right, if your slope was equal to 0 like that, what do you think the correlation is between X and Y? Correlation between X and Y is also going to equal 0. In other words, this regression thing just didn't work out. Why? Because all of your data in this particular situation looks like this, right? Nothing's going on. You just have a flat slope. Your idea of using age to predict income, it just didn't work. Do something else. Choose a different variable. It didn't work. Okay, so that's the most horrible situation. In this situation, B is equal to 0. So let's say that you have different data, you fit the line to it, and then the line looks like this. Okay, this is your new data. It looks like this, and that slope comes out to be 1.5. Okay, so the slope of the new data comes out to be 1.5. Ask a question of that slope. That slope is based on the sample data, right? That 1.5 is based on the sample. Ask that slope a question. When do you want to ask that slope a question? What question do you want to ask that slope, rather?
What's the probability?
Yeah, what's the probability of you, right? What's the probability of you, and what does the slope respond? Under what condition, right? Under what condition? What's the probability of the data under what? The null hypothesis that the true slope in the population is equal to 0. See? Null hypothesis slope, if nothing's going on, this is what the population slope is. But you've observed a slope of 1.5. You've observed a slope of 1.5. So the question becomes, is 1.5 big enough of a difference from 0 that we can conclude what? Okay, yeah, not about an interaction, but I think I get your idea, but that you can conclude what? Keep it, remember this, the statistical conclusion is very, very boring, right? It's very boring. Yeah, you know, if this, hey, what's the probability of this under this condition? Yeah, what's the probability of this in my sample if this is actually true in my population? Probability of this, under this, what could you get? B is equal to 0 sounds like kind of like a what? A null hypothesis. See how it comes out of conceptions, right? You don't memorize what the null is in one particular situation, another you go, that'd make a nice null hypothesis. Then you know you've got the concept, then you can go learn any statistics you want because you've got the concept. So this is our HO, and this we've computed on our sample. So we say, what's the probability of this? What's the probability of B is equal to 1.5 under HO of 0 in the population? Okay. Make sense? So, how are you gonna address that? Okay, again, going into a little bit of review, but how are you gonna, for the final of the concept here, how are you gonna address this question? How are you ever gonna determine the probability of B of 1.5 under this condition? What are we gonna need?
Distribution.
Was it? You need what type of distribution? Sampling distribution, exactly. Sampling distribution of what?
Bees.
Of B's,
Oh,
right?
yeah.
We got sampling distribution of B's. So quite literally, what we're saying is if we had an infinite amount of time and resources, we would say what? Let's go collect more samples. Let's collect more samples. Let's calculate more slopes. Let's calculate more slopes under what condition? Under the null hypothesis. See? Let's go continue, let's go back to the population, which is saying here, and let's get another slope. If I want to know how much this deviates from a null of 0, I don't know, how much deviation would I expect? My God, it's falling into place, right? So I go here, I get another slope. Calculate another sample, do the regression, get a slope. You're cheering for B of 1.5, so what do you hope this looks like? Give me a value.
0.
Yeah, you hope it's 0, right? Okay, it's not gonna be exactly 0 probably. So what do you hope? If I get it and I go, my goodness, this is 20. Good news for you, good news for B? No, why isn't it good news for B? Why isn't it good news? Even that first sample is 20. Why is that not so great news for this? Because what does that first sample of 20 represent? Like the shoulders go down and go, man, I was kind of hoping for something different. 1.5, first sample and building my sampling distribution comes out to be 20, you go, oh, why? Well, maybe it's just 20, let me get another one. 18, yeah, what do you start to think? 30, oh jeez. How's this looking?
Too close to 0.
Right. This is like, boy, again, another one, 5, 4, 10, 15. My goodness, what do you start to observe? You say, my goodness, there's variability all over the place, right? How's this looking now? Special? No. This isn't looking special at all. Variation exists all over the place under this assumption. This is just another piece of the variation. In other words, do you have really good reason to think that the true slope is not equal to 0? No. You got variation all over. Not so special, right? Not so special. Okay. Make sense? Different scenario. Let's start the building of the sampling distribution. I sample. First sample, 0.002. 0.001. 1. 0.8. What's going on here now? Not a lot of variability, right? All of a sudden, the 1 was kind of getting out there, but all of a sudden it's like, hey, this actually does look a little bit different. This might be actually different and actually suggesting a slope different from 0. So maybe this will become what? If I evaluate it statistically, this 1.5 will be what? Statistically significant, right? Statistically significant. Make sense? So the question is, in this case, it's a slope of 0.7. Does B is equal to 0.7 deviate enough from expectation? What's expectation? 0. seems reasonable, it would be zero. It doesn't have to be. You can actually set it to be nothing, but you gotta fight with SPSS to do it, because it's gonna assume it's zero, which is perfectly reasonable. It's gonna assume, we're gonna pretend like the expectation is zero. So expectation is zero, that we can reject the null hypothesis. So we're using big B here for the population value, that B is equal to zero, and infer that B is not equal to zero. So in other words, you're going to do a hypothesis test on the B value. On the B value, and you're gonna see whether it's statistically significant. Okay. Because if the slope came out to be here, right? If the slope came out to be here, well, yeah, statistically that might not work out in terms of the p-value. Comes out to be here, assuming there's not that much variability, maybe you get your p is less than 0.05. So we're gonna need a hypothesis test for the b value to see if it's statistically significant. And what's that hypothesis test gonna be? It's actually gonna be a t-test. It's gonna be a t-test. So right away, as we conclude this course, you hear the word t-test, it's not always about like the t-test for means. T-tests are used all over the place. This is the introduction of how they can be used in regression. What's the t that's being compared? The sample you've obtained, slope, minus under the null hypothesis, right? Under the null, what does this have to be, right? Now, what does that denominator have to be, even without knowing how it's spelled, and we won't have time to go into unpacking it, but what does that denominator have to be? What is it? Standard error. Does everyone get it? It's got to be the standard error. This has to be the standard error of what? Of means? Of B's. Standard error of B's. Standard errors of B's. Now, how did I try to do that empirically? I couldn't do it empirically, it'd take me forever. But what's the standard error of B's? There's a B, plot it. There's a B, there's a plot it. How long do I do this? Forever. I plot the distribution of B's, and what does that denominator tell me?
The average.
But careful, it doesn't tell you the average of them. The average of them will be equal to 0 based on the central limit theorem, and we know the distribution will be approximate normal for a decent sample size. But what is the standard error telling you? Standard deviation of the distribution of the sampling distribution. Okay, this is the standard deviation of that artificial sampling distribution I'm using to assess how probable getting a B is, like the one I've obtained. So, just in summary here, I got the B of 1.5. What's the probability of getting a B like that? I have to do my significance test. And if I reject the null hypothesis, what does it mean? It means that I can infer the alternative that the true slope is not equal to 0. Okay? That the true slope is not equal to 0. So if we go here, right at the bottom, just go there for a second. We have verbal predicting quantitative, right? We have verbal predicting quantitative. Well, let's ignore this constant for a second, because that's going to be the intercept. Look at what this output is telling us. That is the what? There's the 0.70. It's the same one we used in the other notes. That's the slope. That's the slope of quantitative on verbal. So slope of quantitative on verbal. So if I draw it, get something like this. Verbal, quantitative, not a very big slope, but that's what that's representing right there. Right. So you look at that, would it ask the slope a question?
What's the probability?
How probable are you under what? The null hypothesis. Under the null hypothesis that the true slope in the population is equal to 0, that the true slope under the null hypothesis is equal to 0, what's the probability of obtaining a slope like that in my sample data? Make sense? Now, what if this had come out to be 0? What if V here, the slope would have come out to be exactly 0 in my data? Would we say, oh my goodness, I gotta do a significance test on this? No. Does everyone see why? Right? That aligns up exactly with what under the null? Expectation, right? You say that's exactly what we'd expect under the null. So if somebody says to you on the test, hey, you gotta know what your standard error is, or you say, no, I don't. It's exactly with expectation. It's right on the money. I don't care about this anymore, this deviation stuff. It aligns right with expectation. Make sense? Now, for any value that deviates from 0, any difference at all, then, I mean, what if it, let's just go through, instead of 0.7, let's say it came out to be 0.0003. So let's, 0.003. That's what your B came out to be in your sample. How many people look at that and say, well, I don't need a hypothesis test for that because I already know that's so small that I know it's not gonna be statistically significant just because it's so small. Now, you got a B of 0.003 and say, yeah, that one's getting to be pretty big, but this, that's almost like it's 0, forget about it. Give the rationale for why you would still need a hypothesis test for this. It's the reason why you would still need a hypothesis test.
The expectation under the null could still be different.
Well, the expectation, what she said the expectation under the null could be different. The expectation under the null is 0.
It could still be different from the expectation.
Yeah, it is different from expectation. Agreed. That is different from expectation.
Is it something along the lines of effect size?
Well, let's think about it, right? Go through the process. Same thing we did with the sample means. So you got a B of this, build the sampling distribution. Let's pretend like we're building the sampling distribution. So I go here. Remember, I changed the data, right? I changed it so the actual slope is equal to 0.003. Build the sampling distribution. I go and I get my first sample, theoretical distribution. What is this equal to? This is equal to what? Like 1? And it doesn't look good, right? But what if this was equal to, I computed 0.000000000000001. How is this looking? Pretty statistically significant, right? Makes sense, right? Now, one sample is not enough, but it's just an example. So I take another sample and go 0.0000. How probable are you relative to this distribution I'm empirically building, which I never would be able to, but imagine I could. Probability of this is going to be what, pretty? Yeah, pretty high or low? Low. Yeah, low, yeah. Lies off into the tail. Lies off into the tail of the distribution. Make sense? Yeah, you see it? So look, you know, the colleague on the final says, hey, this, I don't need anything, right? Say, yes, you do. You still need the standard error. Because if you're dealing with data that has very, 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 very low variability, maybe that comes out. Maybe that comes out. Right? Maybe that comes out to be statistically significant. Probably not, because as a scientist, you'll know your data and say, oh, forget it. I don't even have to run the significance test. I know it's not gonna come out. But make sure the p-value is still required. Okay. Only in this case, right? Only in the case where this is actually equal to 0, right? 0.000 infinity, it's 0. Does this line up perfectly with expectation? Make sense? Okay, so the rest is we look at we say, well, what's this now? Standard error, there it is. There's the standard error. So this is understood to be a deviation from 0 under expectation. So we take this and we divide it by the standard error, and that gives us our t statistic. We evaluate the t, so we've transferred the data into a statistic, just like we did with z, just like we did with t with means. We're just dealing with a different statistic now, a different problem. It's a t statistic. What do we say? statistically significant, right? Statistically significant, so we say, you know what? Hey, the probability of stuff like this happening is actually pretty low under the null hypothesis. This figure alone doesn't do it because we don't know, right? I don't know, how, is that big or small? If you show somebody is this big, small, I don't know. I don't, statistically, I don't know. As soon as you see this, I have an idea now. You see, because when you look at this, change this result here so that this becomes pretty boring.
0.7.
Yeah, 0.7, right? 0.7, then you get a t ratio of 1. Yeah, you're kind of like just with everybody else. Make it even more boring, right? Question on the test. Change that value of the standard error to make your obtained slope super, super meaningless, boring, and like you found like nothing.
0.9.
Yeah, 0.9. Even, I mean, just be crazy with it. What, make this what?
100.
Yeah, 100. Yeah, 1 billion there, right? 1 billion. Hey, if that's 1 billion, boy, that obtained slope that you're so happy about and proud about, what's your p-value gonna equal to? That standard error is equal to 1 billion. Oh, your data won't allow the standard error of 1 billion, but you know, it's fun anyways, right? So, there's a good question. This matches up exactly what we've done in NOVA. This is review. Standard error, it's like really, really big. What effect is that gonna have on this p-value? Right, it's gonna be borderline 1. It's never gonna equal 1 exactly, always a chance, right? What's the chance? Hey, you know what? This could actually still represent a difference even if your standard error is really big, but the probability of these slope values, boy, are gonna be extremely likely under such a huge standard error. So this p-value, SPSS would probably even report it as 1.0. It's not 1.0, it's 0.999 with a billion nines. But the point is those values become really, really probable under such a huge standard error.
So earlier we talked about how like T and Z scores have an issue with sample size.
Yeah, absolutely. Sample size with T's and Z's, and it's the same thing here.
You still have an issue with that?
You still got it. Yeah, you still have it. So, and we'll talk about that in the spring, but that's gonna be an issue here as well, is sample size can still influence this stuff, right? The fact that we're doing a t-test in a different context does not remove that idea of sample size. So what do we know, right? And you've forecasted the problem perfectly. You said, well, I don't know, like how much weight do we give that p-value? Well, inferentially, we've answered the question. Means that the slope is probably not equal to 0 in the population. But what's the next question? The next question is, well, how big is the slope? Is it meaningful? Does it mean anything to us? So is it possible for this slope to be statistically significant? Yes. If it's equal to 0, can't be, right? Can't be statistically significant. It's equal to 0. I don't care if you got a billion sample size. But if this is anywhere different from 0, that's the same idea as the standard error we just talked about. You see how it's the same? It's the same thing, right? Now we're not looking today at the construction of the standard error, but I guarantee you that standard error is gonna involve a factor of n, right? The n sample size is gonna work its way into this, so that's coming up in the spring. We'll say, look, that standard error, I'll tell you how you can make standard errors low. But this exact point is that this comes out to be different from 0, statistically significant, but the more important scientific question is, does this mean anything to us? Right? Is this meaningful to us? So if I stand in front of the board and I go, look at this, P is less than 0.05, right? Like this, I go, P is less than 0.05, what do you say? You say, well, and I said, I did this on 5,000 subjects. What have I pretty much demonstrated with this? I said, you've demonstrated how you can collect a large sample. Okay. Now, how about answering the scientific question? What's the scientific question here? It's statistically significant.
What's your effect size?
What's the effect size, right? Does that slope mean anything to you? Does that slope mean anything to you as a scientist? The fact that I can take your age and predict income with such weak predictive power maybe that doesn't really mean anything. Make sense? Let's go the opposite. Again, as we get into the review, you see the principles are the same. Let me do this. Huge slope. We'll figure out how to calculate effect size in the spring, but huge slope, the effect is gonna be what? Big. The effect is gonna be big. Did my test, my p-value came out to be 0.60 with that. So this is all I'm giving you, right? I said, there's my slope, it's huge. It's huge. Mathematically, it's just a big slope. It's much different from 0. But my p-value comes out to be 0.6. And I come to you and I say, I thought big slopes should reject that null hypothesis. What's going on? What do you want to look at?
Power.
Yeah, power, right? What's another acceptable answer there? Sample size. Power is the more complete answer because power is gonna involve population variance and sample size. Usually it's gonna come down to sample size, but you're absolutely right. You say, well, your colleague in the lab next door goes, what's going on? You say, how many subjects do you collect? 5? I think that's what's going on. So then how do you interpret it, right? You say, well, I collected 5 subjects. Does that not mean I have an effect? Look, my effect size is huge. Say, I heard that we should focus on effect size. Hey, we criticize the p-value, not criticize it, but what's the deal? What do you tell your colleague, right? Like 0.6, this?
Collect more data.
Collect more data, and you say, well, I don't wanna collect more data, this is enough. I collected 5, each participant cost me $1,000 to collect, cause there is some data like that, we actually have to pay people, and it's expensive. I know somebody who's doing a project, and he has to pay judges, like who have served on the bench for years and years, and they want like a lot of money to answer the survey, right? So he actually has to pay them a lot of money. So his number of data points is gonna be like 10, 20, just because he doesn't have like $50,000 to spend. So there are some data points like that. So in this case, what's the argument for P though? What's the argument for P? So if I'm saying to you, I'm the colleague, I'm going, this is fine. Look, I've got enough I need. Why can't I just stand up in front of an audience and say, look, I have a huge effect. I have a huge effect. What's the benefit of collecting more data as you're suggesting, and maybe if I could afford it, what would be the potential benefit there? I mean, why do we have to please the p-value?
Apply it to the population.
Apply it to the population, does that make sense? Everybody on board, right? Apply it to the population. You say, look, explain it to your colleague, you say, you found this in your sample, but it's based on sample size of 5. In other words, continue. What do you tell your colleague? Your sample size is 5, so
That effect could disappear if you.
that effect could disappear if you collected more of a sample size. In other words, what do you not have evidence for? You don't have really evidence for population slope not equal to 0. All you've collected is 5 objects and observed a huge slope. If you collected more data, as you mentioned, maybe this disappears, right? Imagine data being collected, look what the slope does. You're like, man, huge effect. More data. All of a sudden, your slope does this as the data increases, and then after 100 observations, you find that, wow, this was just an anomaly based on those 5 observations, but I randomly sampled. Yeah, but stuff happens, right? Stuff happens, and eventually, it just looks like this. Then we've talked about the p-value, but boy, oh boy, right? It's a good thing we got this going on. Because at least the p-value is kind of telling you, do you have any inferential support? The whole rationale for the p-value comes into play with this, because then you say, okay, I know why p is important now. So remember, p is important. We just, as your sample size grows, you're not looking for p for an indication of effect. Makes sense? Okay, so just one more thing I want to add before we break for a little bit. We'll discuss this ANOVA table. Okay, there's an ANOVA table in regression, just as there's one in the analysis of variance. So this is not the procedure of ANOVA. This is the analysis of variance table in regression. And what do you think that table is gonna do? It's gonna do something very similar to what the ANOVA table did in ANOVA. Regression, residual. Let's do the comparison, just to make the comparison to ANOVA. Regression used to be, what was it in analysis of variance? Between? Within. Now, it's not exactly the same idea, and we need a couple more months to talk about it, but you see it, right? Like, regression, systematic variation between. The analogy in ANOVA, I'm not saying regression is between variation, I'm just drawing the analogy as to how it works in analysis of variance. Residual, error variance. Leftover, the dump. Right, the dump, then we're gonna compute the sums of squares, and we're gonna say how much sums of squares is due to the regression. How much sums of squares is due to between. Again, they're not the same. You see how I'm drawing the analogy. Don't say sums of squares regression you said is between, because that's not what I'm saying. I'm saying regression sums of squares is analogous to the ANOVA between systematic versus unsystematic. Right? Make sense? Systematic, represented by the regression, represented by group separation, mean differences, to unsystematic. Degrees of freedom, we're gonna have to do some degrees of freedom. What are we gonna get here? Mean squares. What are these? Variances. You're gonna have a variance based on regression, a variance based on residual. Expectation of F should equal about 1 under the null hypothesis. That F ends up being pretty big. Ask the F a question, what's the probability of U under the null hypothesis that the regression isn't doing anything? Basically. And there's your p-value. For this case, since we only have a single predictor, that p-value is equal to that p-value. So, if you're not taking in the spring and you come across regression, you have to do regression. You've got a bit of an introduction to it here. And here's our model summary statistics. You know, we talked about eta squared, r squared. Well, these are gonna tell us how much fit we actually have. All right, so this model is actually fitting pretty good. It's got an r squared of 0.82, and the r squared is analogous to an ANOVA, eta squared. Same idea. I need more time to talk about these things, but you see the principle. Last thing I want to mention about regression is this is simple linear regression. One predictor predicting the outcome, but what's going to happen next, which complicates things a lot. We're going to put in another predictor. So instead of verbal predicting quantitative, we're going to go verbal and analytical. What does that remind you of? You're going to go verbal and analytical. What does that remind you of? Factorial idea, right? Now, that wouldn't be called a factorial regression, but you see the principle is the same. Say, well, I see, instead of one predictor predicting the outcome, you want to do two predictors simultaneously. And the reasons for that are what the next course is about, as to what a lot of complications arise with that we can talk about, but you can do it. So when you come across in your research labs, you go, well, I've got verbal, I have analytical, two predictors simultaneously predicting the outcome, then you're checking them for statistical significance, etc. But to understand what those mean and how this works, and like I say, as soon as you put in more than one predictor in regression, the whole sky opens up, and there's a lot of issues we need to talk about. So that's what we're going to talk about in the spring. Okay. But it makes sense, all right, in terms of what we've looked at, and hopefully some of that also likens it. You see the parallels, right? So when you learn new stuff, it reinforces the old, because you're like, oh yeah, that's actually the same things we were doing before. And if you take the multivariate course, you'll see that even more. You'll understand why these things all fit together. And then you stop looking at things in terms of ANOVA, regression, and you start seeing it as a bit of more global thing. Questions on this? You're like, just get to the review, damn it. You have questions on this? No? Okay, so why don't we take 15, 20 minutes, just take a break, refresher break. We'll come back and then we'll talk a little bit about frequency data, because I want to talk about frequency data just for a little bit, and then we'll answer any remaining questions on the study guide.